Hello, my name is Baturalp Ergin. It's my second year in Bilkent Physics department, and today I will present you my Physics 211 project. The name of my project is analyzing model analysis of sound waves using Chladni plates. The objective of this experiment is to visualize the sound waves on 2D metallic plates. And we're choosing this project because it's visualizing the abstract mathematical equations and abstract wave theory of abstract physics wave theory visible to human eye. And secondly, this theory includes a lot of topics from our lectures as well, such as linear algebra, differential equations, elasticity theory, and most importantly, wave theory. Secondly, I need to mention you briefly about the history and the theory of the experiment. The first one to perform this experiment is Ernst Chladni. In 1787, Ernst Chladni used a violin bow to excite a metallic plate, and he sprinkled some sand over the metallic plate. He observed that the sand is accumulating along some nodal lines when he excited the metal plate at some specific frequencies called Eigenfrequencies. And secondly, after Ernst Chladni, the Gustav Kirchhoff improved the theory so much. He applied the correct assumptions and correct boundary conditions to the apparatus, and the assumptions, some of the assumptions are the no thickness change of the metallic plate during the vibration, no transverse shear force, and negligible transverse displacement. Additionally, he gave the equation last form as well, as you can see. This is a fourth order biharmonic equation. Because it's a fourth order, its analytical solutions are limited, and due to the lack of analytical solution, we will use COMSOL simulation tools like COMSOL to solve this equation and look for the solutions. COMSOL is using finite element method to simulate to create a digital copy of the material and the plate setup and dividing into some triangles, and then applying correct boundary conditions to solve the equation. Creating small triangles and applying the correct boundary conditions then. Now I will introduce our setup. Our setup is starting with a power supply. This is a 12-volt power supply, and we are using a PC-based signal generator for our speaker, and we have an MP3 circuit, an amplifier circuit to connect speaker into the PC-based signal generator. We have our experimental plates. We have 3 plates, 15 to 15, 25 to 25, and 30 to 30 centimeter plates. We are using aluminum 5000 alloy because its density and high elasticity is more suitable compared to its rivals like steel, brass, or glass. And we have a modest mounting mechanism which includes a threaded nut with a threaded bolt nut and a plastic cap. Now I will and also we are using salt as a granular material. Now I will show you how our experiment works. We need to make sure it's totally flat. Now we will pour some salt. Now we are starting from 100 Hz. You will see how the the salt starts to vibrate when we are getting closer to eigenfrequency. Yes. Now we are at an eigenfrequency 125 Hz. As you can see, there is a double line forming. As you can see. Now we are getting to 127 to another eigenfrequency. In this eigenfrequency, as you see, this is a circle is the circle nodal shape is producing, and when we move, you will see how the sound decreases and increases when we are getting closer to another eigenfrequency at 300. At 60, we have another eigenfrequency. It's like a square, like one square and small circle. It's like a grid shape. And when we go to 600, we have another eigenfrequency. This is like a propeller shape. Also, there's here as well. Yes. This is like a propeller shape. Of course, the shapes and the results are a little bit distorted because of the source of error. This source of errors include the mounting mechanisms is not fully mounting the plate, and also there is some horizontality issues, that is also gravity is included, and lastly the elasticity of the plate is not fully as well. Thank you for watching. This is my Physics 211 final project.